Now I would like to talk about the topic of our recent work, which is the security implications and new attack vectors against LLM integrated applications. Before we dive in, let's kind of review how we were back in the day, like ancient history, only a couple of weeks ago, or a couple of months ago, how we used to interact with LLMs and what we have now with applications. So before we had some sort of a clear input channel or clear instruction channel. So the user is communicating with a large language model such as ChatGPT by giving instructions and asking questions, and the model replies or responds back. So it's only one input channel. And of course, there were some risks. So for example, a user might exploit the model to generate something that it was trained not to do, or maybe to automate some malicious tasks, such as the creation of disinformation. However, overall, these risks were kind of relatively bounded because the models were not able to react or to act on the external world, so they were only responding. And at the same time, the attacks usually affected one instance of the model, so they couldn't affect other users using the same model. So now with the current setup of using LLMs in applications, LLMs are no longer a standalone unit or a standalone system. So based on the application, they are fed with external input at inference time. And this could be search results, emails, and so on. However, there is little or almost no control over the input that the model can digest, and therefore these retrieved inputs can be untrusted. And the key message of our work here is that this setup of having LLMs in charge of applications and ingesting external retrieved input, this setup essentially blurs the line between data and instructions. So the model now, the attacker now can indirectly prompt the LLM, indirectly prompt the model by placing some prompts or instructions into data likely to be retrieved at inference time, such as web pages or emails and so on. Now, when the user starts to interact with the system and starts to ask questions that require some sort of retrieval of this external data, the model will ingest these external inputs and will also ingest the prompt, and the prompt will start to steer the model according to the attacker's goals without the user knowing. So once we establish that this is possible, that it's possible to feed instructions indirectly to the model, we then ask the next question, like what can the attacker practically do? And for that, I think we need to remember that current LLMs or current models are sort of general purpose models. So they are not trained to do a specific task. Like they are not, for example, a sentiment analysis classifier or an image classification model. No, they have very diverse capabilities and functionalities. So based on that, the attacks as well will have a broad range of diversity and different goals and different setups and so on. Because the way we modulate these models are by natural language instructions, right? So we, since the capabilities and functionalities of the model are very diverse, so we modulate them with instructions in natural language. And if the attacker is able to give instructions to the model, then the attacker can also modulate the functionality of the model by natural language instructions. And because of this, I really argue that any functionality the model can originally do can be attacked or can be exploited to achieve the attack goals. So kind of in a computer security terms, processing these retrieved input data with the prompts in them would be similar to executing untrusted or untrusted code or arbitrary code execution. So just as a motivation of why we should really care and should really be alarmed about these new attack vectors is that these models, we are witnessing them being integrated everywhere at really an alarming fast rate, like on almost a daily basis announcement. And these applications are currently being used by millions of hundreds of millions of users worldwide over on a even on a daily basis. So given this huge user base, we should really be alarmed, because now one attack can affect millions of users instead of having one attack only affecting a single LLM. And not only that, but LLMs now are even being used in very high stake and security sensitive applications like legal domains, medical domains, even governmental defense, or like ironically inform the decision making of security experts in order to improve the security of systems. So now I hope I convinced you that there is a problem and we should really care about it and should really be alarmed. So I would like to walk you through the details of the attack themselves, or the flow of how attacks can be implemented. So now we assume an attacker. This attacker can attempt to indirectly prompt or steer the model by placing prompts into data likely to be retrieved at inference time. This could be emails, it could be web page results, or poison documents if the model is offline, and so on. And for that, I would like to highlight that with new applications that have several channels, several input channels, or even models with new modalities, we really open new grounds for attack delivery. And I will talk about this later and give some examples for this. Now, when the user starts to interact with the system, like tell me today's news, or give me some search queries, and so on, the model attempts to retrieve some data, and along with that, the prompts are also retrieved. And after this point, moving from this point forward, the attack process will really depend on first the application and the attack's goal. So if the model or if the application has access to APIs, they can be used to allow two-way communication, or maybe automated data exfiltration back to the attacker, or they can be used to cause unwanted behavior in the user system. Or as I will show later, the attacks can also be used to manipulate the models, the users themselves. So it seems clear that there are so many possibilities of how attacks can be delivered, and also the threats that they can cause. And in order to study that in a bit more systematic way, we draw some insights from traditional security principles in order to categorize the attacks by first the technicalities of how they can be injected or implemented, and also the threats that they can cause. So they can cause maybe privacy leakage, information gathering, data exfiltration, or they can also facilitate frauds such as phishing. They might also be used to gain unauthorized access to the user system, or call other APIs, and so on. Or they might spread malware. And the new insight here is that actually prompts themselves are malware. So they might spread injections like similar to computer worms. And also we will show that the application functionality itself can be manipulated. Like in case of search engine, the summary of the search results could be manipulated to be wrong or biased, and so on. And finally, similar to also security principles, attacks can be used to cause denial of service or other availability attacks. So now I would like to show some examples of the attacks that we have implemented using this taxonomy. So the attacks kind of instantiate from this taxonomy. So they are not really exhaustive because, as I said, there are possibly a lot of different ways of how attacks can look like. But I will give some highlights of observations that I think are worth sharing. And of course, like I invite you, if you're interested to know the exact details of the attacks, or maybe like to check the exact output and also the prompts that we have written to deliver these attacks, you can find all of that in the paper. So to test the attacks, we have tested them on Bing Chat as a sort of a real world system. And we have also developed synthetic applications using GPT-4. So these synthetic application simulate like a personal assistant model that can, for example, read and send emails, write to memory, and so on. So one thing that I would like to highlight here is that the attacks really need minimum instructions. So they don't need to be like scripted in full details. No, it's just like by outlining the goal, the model can autonomously execute the attacker's goal in a dynamic way that's actually adapted based on the context of the conversation. So in here, for example, this the prompt is instructing the model to convince the user to disclose their name and then follow a link that will lead to data exfiltration. But the model, in that case, the Bing chat, based on the information gathered from that session, it adjusted its persuasion behavior to make the persuasion personalized to the user and to the context of the current conversation. Also, as I said, attacks can be used to automate frauds or automate other phishing scams, for example. So the use of LLMs in cybersecurity attacks has been like considered as a static way of, for example, creating phishing emails. But with chatbots, the attacks could also take like a dynamic, automated social engineering way, and they can also enable new distribution vectors of attacks. So in here, the prompt, for example, redirect the user to a phishing page that should look like an Amazon web page that the user should enter their credentials into. And by now you might think, okay, these really look weird. No one would fall for these attacks. But I think I would like to remind you of some few points. The first thing is that we really didn't solve traditional phishing yet. So we still have huge financial losses every year due to phishing. This is one thing. The other thing is that the exfiltration might be automated in the future if the models can send, for example, emails or other sort of APIs directly without the user involved. And also this is a new territory, right? So by now users might have learned that they shouldn't trust random emails delivered to them, but for users, this could be like an official Microsoft service, right? So any output generated by this could have some authority of being official. And also the last thing is that, well, future models can be strong persuaders, and there are already a lot of discussions nowadays that deception might emerge in future models due to as a side effect of training, such as reward hacking and so on. And also the last thing is that attacks can really be stealthy. So for example, this attack simulates like a malware distribution thing. So the prompt instructs the model to sneak in a malicious link within the answer. And actually, these two links are genuine parts of the answer. So these are actually legitimate links to suggestions of book recommendations. And this last one is a malicious link, or like a simulation of a malicious link. And really, you cannot tell. They seem so native to the output or to the functionality of the model itself. So it's hard to even tell. And sometimes the attacks could be really sneaky. Yeah, again, I'd like to take a pause, and if you have any questions so far, please let me know. Just unmute yourself and please ask any question you have, or maybe also ask in the chat. Okay, I think I'll go on, but please stop me at any moment if something is not clear. So I guess we're moving on with the threat taxonomy that we have. I guess the next point is intrusion attacks. So intrusion, we mean by this, any attack that aims to gain unauthorized access to the user system by calling other APIs or by controlling the system infrastructure itself. And now we might actually observe that there is a recent trend of having autonomous agents that they can call other APIs, or they can do tasks autonomously. And I think that we think that this would constitute really a vulnerability or a backdoor for attackers to gain unauthorized access to the model or to the system infrastructure as a whole. So as a part of example of intrusion attacks, we simulate attacks with models that are able to read and write into some sort of a memory. So this is to simulate the model has a chat history. And this is a feature that has been actually discussed nowadays with many plugins. I think it's already available in ChatGPT plugins, and it's also now, I think, will be added soon. I'm not sure if it's already added, but it might soon be added to Bing Chat as well. So in here, we simulate an attack like we start with a compromised LLM, and the injection instructs the LLM to write the injection itself into a memory. And then when we start in a new session and the uncompromised LLM starts reading from the memory, the injection is reactivated. So it means like the attacks can be persistent even across sessions. And I already talked about phishing and also malware. And I said that LLMs can now facilitate the distribution of web attacks. But the new threat also here is that prompts themselves can be seen as a sort of a malware or a computer worm in that case. So we simulate an attack here with an email client. So an attacker sends an email with instructions, and the instructions here involve forwarding this email to all users or to all emails in the address book of the user. And here it essentially means that the attack can replicate itself or can actually automatically spread by spreading other LLM. Okay, so far, well, I talked about attacks that we can think of them as like a side task, right? So they do a side task to the application functionality. But I also would like to show some examples showing that the application functionality itself can be attacked. This is really relevant because models now, like in search engines, they really act as a vulnerable layer between users and information, and users might still over-rely on them or take information from them without verifying or checking. And also, I think there is a really important point that I would like to highlight here is that people have been discussing whether LLMs is dangerous to spread this information. And I think there are some people some people believe that the creation of this information is really not the key factor, but the distribution or the dissemination of this information is the important distinguishing factor in influence campaigns. But I think here now LLMs and search engines can really do both. They can generate this information even dynamically, and they can also spread it to millions of users, given potentially the huge user base of these systems. So we show that it's so easy to manipulate the search results, right? Or the search summaries, at least. So for example, we have attacks that produced biased output towards a certain affiliation defined in the context of the prompt. And we also found that just by defining vaguely the affiliation, we can extend or generalize to topics that were never mentioned in the prompt. We also show that prompts can deliver wrong summaries of search results, which again, by not mentioning any topic in the prompt. And we found that in that case, the model still provided inline citations, which would give a false sense of accuracy, because sometimes people might not go and check the cited links to see if the summaries are correct or not. And also something that I found actually interesting is that the prompts can cause follow-up actions, right? So once the prompt is injected and activated, it might affect the output, and this will in turn affect the follow-up output. So it's sort of like a feedback loop. So in here, the model, for example, issued new search queries that were affected so far by the context of the conversation. So the prompt continue in a way to steer the output actually according to the attacker's agenda. And one thing also that I think worth highlighting here is that the output can be partially true, because the model relies on its internal knowledge and also the retrieved input. And therefore, it could really be hard and challenging to draw the line and distinguish between the facts and disinformation suggested by the prompt. And also, the one thing that worth mentioning here about search engine is that the prompts are now kind of a new way to hack search engine optimization. And for example, this can be used in recommendation systems, or can be used in forcing promotions that maybe are unfaithful or also undisclosed as promotions. So moving to the last threat, I think what I wanted to highlight here mainly is that models are responsible to calling and issuing other APIs and also forming the arguments to the other APIs. And therefore, these input and output operations can be attacked. So for example, here, the attack instructs the model to replace all characters in the search queries with their homoglyphs before searching with them. And this basically renders the search or the retrieval overall ineffective, because this will end up with having unrelated or irrelevant search results. But the dangerous thing is that the model still hallucinates. So here we can see that all the search results are related to the time, because the only thing that was not corrupted in the search query is the year. But still, the model hallucinated wildly some wrong things based on the search results, or like the search results. And also similarly, we can instruct the model to corrupt the search output before formulating the answer. And this also leads to a similar observation of hallucination. And finally, like, availability attack can be embarrassingly simple. So we don't need to optimize sponge examples, sophisticated ways to make the attack run longer. We can simply ask the model to do a meaningless task in the background, right? And this often resulted in a timeout or a very increased computation time. Or maybe even instruct the model to be not helpful at all. So there are so many ways of how to actually break the availability or break the service. And this could be alarming if it's combined, for example, with persistent attack in order to affect the model, not only for this session, but also for future sessions. So this concludes all what I wanted to say in the threats. Now I wanted to highlight some challenging ways or even some advanced ways of how these prompts can be delivered. So how to hide the prompts as like advanced injection methods. And I will conclude with some discussions of mitigations. So one thing surprisingly that we found here is that instructions can just be encoded, right? So we encoded here a prompt and then simply ask the model to decode it. And this, we can think of this as really like a cascaded indirect prompt injection, or like a second order indirect prompt injection. And despite the encoding, the injection was also successful and the attack succeeded. We also simulated another case or another hidden injection method, is that the attacker can insert an initial trigger, initial injection in a public website, and this instructs the model to go and fetch another bigger payload from an attacker-controlled server. And this could be used to hide the injections, for example, from manual review even. And for that, I would like actually to highlight this. This was released last week by Anthropic. So they highlighted this, is that when they fed a huge context window of like an entire book of 70-ish K tokens, and they changed only one line, the model was able to identify the one line that was changed out of this huge context window. So it means that potentially we can also inject some sneaky prompts in these very huge context windows. And related to the second order injections, I think Python interpreters and other plugins can be used to enable adversary chosen encryption techniques and to provide further concealing of the prompts. So now the use of interpreters were assumed to be safe because they kind of run in a sandbox environment, so they cannot affect the user system, but they can be used to bypass basically any filtering defenses or filtering techniques. And for that, like there were some users that actually shared some attacks that they have done based on indirect prompt injection. And for example, this attacks, first it shows that we can apply the same attacks to other plugins, to other systems, not only Bing Chat, not only GPT-4, but also things like ChatGPT plugins. It can also that indirect prompts can be used to invoke another plugin. In that case, it invoked an Expedia or a flight plugin. So this could be, for example, Python interpreters, or could be any other plugin available. So I would like to conclude with a short discussion of potential mitigations. So we might have seen this kind of arms race of jailbreaks and adversarial training, and it seems like this is hard to solve. Like we didn't really solve the adversarial vulnerability evasion attack after 10 years. And this could also be similar of evading jailbreaks and evading adversarial prompting. But some solutions suggest, okay, let's just detect instructions from the input data. But I think this is also not easy as it sounds, because first, we don't have really a formal way or a unified way of how prompts or instructions can be written. So they can be written in different languages, different formats, even different characters, and we really cannot control that. So it's not so trivial to filter them out. And the other thing is that, as I talked a little bit about this, is that the instructions can be encoded, they can be hidden, or later in the future, they can be in different modalities, like in visual prompt injection. So again, it's hard to control. And if we use another LLM, if we throw in another LLM to detect instructions, this second LLM can also be evaded similarly to the first LLM, right? And the last thing that I think is also important is that models can be vulnerable to priming, right? So we might have seen this example from the early days of Bing Chat, where Bing Chat started to get hostile and offensive against a user after it actually ingested the user's Twitter tweet. So in here, no explicit instructions are involved or given, and this was like unintended behavior. But an attacker can do something similar, is to control the or bias the output of the model just by some controlled way without involving specific instructions. And other solutions involve, let's detect attacks without actually detecting the input, which I think, okay, this might have some potential, but again, we have really a broad way of how attacks could look like, and it might be intractable and hard to list and control what kind of attacks can be delivered. And this also, again, seems hard to do. Maybe a solution is to restrict the functionalities, restrict what models can originally do, but the question remains, how much can we take from LLMs? How much can we take from the current models and restrict them while still being interesting to users? Because I think currently people are interested with these models because they are super flexible, they are super powerful and capable. But if we restrict them in order to, or limited their functionality in order to ensure the security of systems, will that still be first useful and also exciting for people? So my main message is that I don't want to sound really pessimistic, but I guess the main message that I want to say is that we should really be careful before claiming and jumping to the conclusion that this problem is easy to fix, because it might not be as easy to fix as some people claim or say it is. And I think the final notes, like I would like to conclude with final notes is that even without attacks, even without adversarial prompting or anything, LLMs in applications really pose current risks. Like in this example here, one chatbot used the output of another chatbot as a source of information. So it's kind of like an automated way of misinformation ping pong that are shared between different chatbots. And also, people might over-rely on their output, like in search engines, for example, but the output is not always truthful and it's not always supported by the search results without any adversarial prompting. So I think we should really stop and ask ourselves before getting so excited about these models and these applications, these new technologies, is this kind of an online world that we want to build where one AI model fills the internet with other potentially other AI models output, and is this a way that we want to verify the information? I think this really might add a whole mess to the even the current information manipulation ecosystem. So we kind of really suffer from misinformation at the moment, and with all of these technologies, these risks can be further amplified. And really, the final message that I would like to say here is that these attacks are here. They constitute current risks. These are not future risks that might or might not happen. And they're also so easy to implement. So usually in adversarial machine learning field or machine learning security, we study attacks that might involve sophisticated optimization techniques or maybe some unrealistic assumptions like knowledge about the model, knowledge about the training data, and so on. But these are so easy to implement. They almost don't require any knowledge about the models. And they also have high rewards for the attackers based on the sensitivity of the application and also the huge user base of models. So essentially, this is kind of a sweet spot for adversaries. And I think we should really not wait for reported huge world damages and losses from these attacks before we realize that we should start acting on them. So this concludes my talk today, and this is all what I wanted to say regarding this threat. And thank you so much for listening. I hope I didn't take so much from your time. And please let me know if you have any questions.